about this from the beginning, but a quick one. When you're dealing with machines, whether it's a router, it's a plasma, any kind of machinery which is heavy grade like what we're dealing with, it's always important to have a couple of things to protect yourself. To start with, can I have this? Whether it is a CNC router for cutting wood or it's a plasma for the metal, it's important to always have glasses, which will protect your eyes. You're protecting your eyes from two things. First of all, it's the plasma beams that you can see these coated glasses like this would do very well. Or you can also get what we call welding glasses or laser cutting glasses. Those are good enough for plasma, number one. Number two, the chuck which is being extracted here, all of that cut metal, which is very small that you're breathing it in, same thing as the CNC router. So you'd also want masks to protect your eyes with the glasses and then your nose from that offcut that you are getting that is being taken out. So from the smoke and all of that, a mask would be important, and the dust. The glasses are to protect your eyes from all those tiny pieces which have been cut out. And lastly, another crucial thing would be gloves. Whatever you're doing, as long as you're handling rough material, you'd need gloves. So at least have those three things. Those K95 masks, if you can get any higher grade than that, that would be perfect. But masks, gloves, and some glasses to protect you, that would be crucial. Thank you.
Yeah. Okay. So on this part of the video, or on this video, we're going to be talking about the CNC router. Now normally people hear CNC, then they're associated to a CNC being a router. CNC basically means computer numerical control. You can have other CNCs. You can have CNC lasers. You can have CNC plasma cutters like the one right here, which is basically a computer numerically controlled plasma cutter, meaning power is coming from the plasma. The difference with this system and this is we still have your 3 axes, which is your Z, up and down, Y, which is the longer arm, and then X, which is the shorter arm on the horizontal axis. Now with this, it's still CNC, but now, instead of using a plasma power supply, as we did in the other previous videos, we're now using a spindle, which rotates what is called a router or a routing bit. Right, with that being understood, I'm going to move around the machine and explain everything in a short segment of this video, but now let's watch everything as to how we're going to train the guys, starting from the most important thing, which is tool change. Okay, you can come closer. Okay guys, let's start. Okay. So to start with, this is your spindle, right? Remember, everything we talk about CNC on the plasma is the same here. X is still X, that's X plus, X minus, Y plus, Y minus. The homing position on all of the CNC machines that I'm going to train is always bottom left. So which means if I say go to 0, 0, the machine is going to come here. That's the bottom left. With that being understood, first thing which I consider to be important is changing the tool. Changing the tool is important because how you place it affects almost everything. If I don't place it wrong, it breaks. It's going to throw, it's going to jump off. Whether someone is rotating, they can go to hit someone. Remember, this thing is rotating at 24,000 rotations by minute. If you do the maximum speed, which is your speed number 7 on this program I'm going to show you. But 24,000 rotations per minute, and it just snaps. So it needs to be tightened properly. And also, your bit affects all of the work that you're going to do. I'm just going to put this in the frame as well and what's happening. Now for me to change, we have 2 spanners, right? Mike is going to show what's happening here. I have a size 30, depending on the machine that I have, of course, which holds the lower part of this holder here. And then I have the smaller driver, which basically holds this. There we go. So first thing is I just want to get rid of the tension here by simply doing this. Once it's loose enough, I'm done with my tools. I'm now going to rotate this and take my tool out. Now I've taken 3 things out, which I'm going to explain in detail. But I need you to see something. There's an e-stop message on my pad to show you that anything I'm doing now, nothing is going to move because I don't want the mistake of touching this and someone by mistake turns on the spindle and I lose my finger, which is already its way out. Alright, now, you have a bit, right? That's your router bit. Your router bit has a thickness it has a shaft and it has the cutting zone. So the whole thing, if you measure it, is the length of your bit. These things are important to know when you start with your cutting. You need to know, okay, how long is mine? Because that helps you determine how deep can I cut. There are shorter bits, there are longer bits. And if I need to clear something, if you see this is about 16 millimeter MDF, if I check, you can see my outer bit again, cleared. If I get something shorter.
Yes, absolutely. Maybe we use that other.
Yeah, yeah. Alright. Now, as we're explaining about our router bits, we have different grades, right? You see this one has a spiral edge. This is what you call a spiral bit. Now, spiral bits come in three modes basically. We have what you call an upcut, what you call a downcut, and what you call a compression bit. I know it sounds complicated, but it's really not. But you choose this according to what you're cutting. Wood MDF is fine because it doesn't have a grain structure, and that it's synthetic. So it doesn't have, if you deal with natural woods, your hardwoods, your muka, your pine, acacia, you find out that if you get into furniture, the wood has a certain direction that's inside. So you want a bit that also kind of works hand in hand with what's going on inside. Now, what makes this one, or how do you choose? This bit is a downcut bit. Downcut bit, when my bit is rotating, all that dirt is going to shoot up. It's going to go down. Do you understand? Ideally, downcut bits give me better quality. Why? Because the edges of the bit don't really play much with the material because there's already that chaff that's already down here. And downcut bits, people prefer them because they don't shoot up a lot of dirt in the air. Put it on the material. However, the question then becomes, but then how do I keep cutting if there's a lot of dirt on the board? That is why we have a suction system that we're going to be talking about here, which sucks up all of that dirt and puts it in the dust bags here. So this is basically a suction pump. That's what it is. So you have upcut, downcut, and compression. I prefer compression bits. Compression bits basically have an upcut and downcut. So instead of putting everything out here into the material, they drop the material. Like the offcuts stay somewhere in the middle because they have a combination of both upcut and downcut. So it deposits the material on the surface, not in the material. That waste or the spillage that you are cutting off. Ideally, for most of your cutting, because you have a lot of these, you're going to be working with these types of bits, which are upcut. The quality of your downcut bits, actually, the quality of your bits depends on a couple of things. Number one, the material that is used to make. These are tungsten carbide bits. They are one of the top grades in CNC routing. If you have a poorer quality bit, it's going to break off. And I'd like to put a disclaimer. Bits are going to break. That's okay. It will happen. Plenty times. It's not supposed to, but when you're learning, it will happen. And sometimes it just happens because the bit is tired. It breaks, it overheats, it snaps. But you always want to make sure that it's not because of how you placed it. If it breaks normally out of it being worn out, it doesn't shoot out. But if it breaks out from what it's seated properly, it shoots out and it will hurt something. Okay, so we talk about the bits. This, you just measure the thickness. The thickness of the bit, you don't have to struggle, you only measure it. You take a vernier caliper, this looks like a 6mm bit. Is there a vernier nearby?
No, but I think it's 2.
Yeah. So ideally you must know the thickness of your bit if you want to know the thickness of what you're cutting. Because on your software it's going to ask you, do you want to cut outside the design or inside? And if you say outside, go 60mm outside, which means if you had a smaller bit or a bigger bit, you're going to use the size item. So bit number one, that's important. Again, the length of your bit, like we said, matters. You see, this is a shorter bit. It's not going to travel well. Because if you want to cut good, go already with this of the bit. After that, we have other bits. This is called a clearance bit. Where a clearance bit comes in is, especially if you're using a vacuum table, it would have made more sense. So the material you see now is called a spoil board or a spill board. This is not what you're cutting. this is what you are using as a mattress for what you're cutting. When I'm cutting through and I want to cut through. You get, I want to go beyond cutting. It means it's going to have to cut through this board here. Not through, but it's going to have to cut on this board to touch it. And that's okay. We do this to protect our bed. So now imagine if the bits were just cut through nicely and gone through, and there was no board to go into there. And then the route is moving, getting in and it breaks. But either the motors here, it breaks the bit. So that's why we need a spoil board. The thicker the spoil board, the longer it lasts and the better it works. The problem with spoil board is you're going to keep on drilling them, over time you're going to not just walk, but you're not going to keep it. That's where this big board comes in. This is called a clearance bit. The whole point of this is it skims the entire surface. You're going to do this when you're dealing with tables, when you're dealing with anything that has a wide area that needs to be planed, flattened. When you come to doors, this is going to be your best friend. So you take it on the top, you set the 0 position, and you do what's called an array. An array simply means you tell it to go all the way there, come back until it gives you a smooth surface on this. Because remember, you always want to have this height even throughout. So that what you're cutting is the same thing you're cutting there. Sometimes you just do it one day. Are we together? That's why you also have to have it to be the same area. You find out that this will be the most used part of the machine. It will actually be more worn out than at anything. So we use this sometimes to just skim the whole surface and have an evenly leveled surface. That's the clearance bit. You have bits like this, which are just basic cutting bits. It's as good as this, but this gives me a smoother finish because of the spirals. This gives me a rougher finish. If I was to put it in other layman terms, I would say this is soft and this is a bit hard. That's the whole point. Right. You're going to get other beats and in different thicknesses. Smallest you can get up to a 1 mil bit, but your base determines the speed at which you're cutting at. If I'm doing a lot of cutting, I want a thicker bit. Why? Because I want to clear the area faster. Whereas if I take a 2 mil bit, I have to move at a very slow speed and do a lot more passes just to get a small circle out of this. Whereas if I have a 6 mil bit, I can go deeper and faster. Okay, so that's it on bits. I see you guys are getting tired already. Alright, the next thing is called a collet. The bit doesn't go straight into the machine. The bit goes into a collet. The collet is what goes into the machine. Right, collets are specific to bit size. Some of them have a range, some of them don't. Some of them are written, and as you can see, this one is 6 to 5 millimeters. So 5 or 6 mil can get in here. So I take my bit and I put it into the collet. Now remember, you want to put enough so that you can have enough cutting area. At the same time, you don't want to put too little to a point where when it starts moving, it's going to break. So I normally put it just until I can almost touch it here. But ideally, you want longer bits. 50 millimeter bits, normally very good. This one looks a lot smaller than 50 millimeter. 50, 60. The longer the shaft of your bit, the more, the deeper you can go with your cutting. So ideally, you just put it. For me, I can go halfway through, somewhere like this. Perfect. And then from there, this is just rolling out basically. So this comes in here. Once it's seated, then I insert it into the bit. And then I tighten it while I'm looking this. I'm holding it so that it doesn't move. Once I can't move it with my fingers, then I take my 2 spanners. I hold and lock the top with whatever the correct size, whichever one has the correct size, which is not that, but it's really this. Okay, cool. And then you just take this one. And you're locking. Remember, to unlock, these things come together. To lock, they just open like this. Now, don't tighten it like a madman. Why? Because you can break the bit. And the dilemma is now people think, well, if I don't tighten it too much, won't it get loose? Just tighten it enough until I can't easily move this. That's good enough. Okay? So I'm going to have one of you guys open this and re-put the bit, and then we can go to the next part. But I hope you understood about collets. It's very important. See this collet here? That's 1/8 of an inch. That's what it means, 1/8. It doesn't write anything in millimeters. I think it's Yes, there's an area of this. But all I need to do is open it using the best tool given to mankind. But alright, if I open it now, there you go. And you try. I don't think it's going to work for. This is for normally 3 more bits going down. So you see, collet matches bit. So when you're ordering your bits, remember to order with collets. Okay. Apart from that, does anyone have a question yet? There isn't much. You get different tools for different things.
Sorry, Mr. Bruce.
When you wait, see ER20, so it's a 20 millimeter thick collet, but 4, so it does 4 millimeter bits. And if you don't know, just take it, test it. Now, when you are choosing your tools, you need to understand what you're working with. For most of the cuts you're going to do, spiral bits are going to be good enough. There are what are called bonus bits, which I prefer. Bonus bits don't have a sharp end like this. They have an end that is like a bone. That gives me some effect at the bottom. But it really doesn't affect much for you. You're good enough. Most of your cuts are going to be accomplished by these two bits. Most of them.
This can also do right through cuts.
Yeah, right through cuts, engraving, but bonus bits are more amazing for engraving. So you understand, if I want to engrave with a bit like this, I'm going to start because there are these which are called flat end or bonus. The flat end, it gives me nicer engraving features because it's not like it doesn't have a sharp end like this. It has a flat end, so I can be able to write nicely what I want. So this should also help you when you're ordering your bits. As long as you get a bit with a pointy end like this. It can engrave, but it's not the best thing for engraving. You want bonus bits, flat bits. Bits. V-carve bits are for, they are what we call, there are some very specific functions that we do with the router. For example, there's what we call creasing. If you guys remember, people will cardboard manufacturing. You use a CNC router for making the creasing lines. So you need a special tool which is called the creasing tool. It's basically a router bit, but it has a wheel. So you just run, it goes in the turn of where the card boxes are going to turn on, and then you can now forward it. Stuff like that. Those are the other things. As we go forward, you learn more of it. But V-bits, you normally use them when you're doing things like what you see is for etching. Things like glass and stuff like that. Your router bit will be rotated. It will just be etching. And maybe you're doing it just like a drawing between the person and an artwork. Yeah. Well, I wouldn't just we want something a bit stronger in terms of, but it's a good question that you actually bring about. What can you do with the router? You can do a lot. As long as it wood, perspex, right? You can do tombstone or granite. That's actually what it's not just for dead people, but you can write it. There are more specialized routers that we use for tombstones. But if you have a small job, you can do it. You can do it on this one. The specialized ones will basically be this. It can even be the same spindle, but two things will be different. The bit you're using will be a lot stronger for ceramics. It's a ceramic bit that you can use. You just go to where the supplier, I want it before, choose to go for ceramic, and then they'll give you a granite bit or something like that. But number one, apart from the two, the second thing that it will have normally what you call a water bed. Why? Because you need to cool it.
So let me just explain a few things. You see this box here, right? Oh, this, I can't call it a box, whatever it is. This is a dust collection unit. The whole point of this is it runs air through all of this, and then it comes through to this part, which is your dust collector. These are what are called auxiliary components, in that the machine doesn't need it to work. It's simply for you to extract and remove the dust, that you don't have a lot of dust inside here. Ideally, it fits this way. You can put it whichever way you want. Other people put it on the side, other people put it on the top. It's all up to you. And then it has an Allen key here. I do not see the Allen key, however. That's probably why I was able to get it off easily. So you simply mount it here, and you see the brush bristles that are here. The main reason for the bristles is so that it can actually sweep off some of the stuff, and then it can suck it up. And also it creates a complete vacuum. It covers so that air is not escaping when it's sucking everything. It's properly taking everything. If it's locked and tight, that actually would work better. But now it's not even tight. So if you don't mind, I'm going to leave it hanging here. It's okay. Number one. Number two, you have your bit, everything, the quality inside. This is your spindle, right? This whole thing, it's a whole motor, right? The spindle. From there, you have your tracks where everything is running. A router is a very robust machine. There's not much you're going to damage apart from changing bits. That's pretty much the only thing. But you have to oil your machine regularly. There's an oil jack here. I don't know if you see it. Right. So you fill it with oil, and then you'll be pumping here to move it down. And then someone with a remote will be moving it forward, back, until you see oil running all the way through here. Any form of mechanical oil will work here. Okay, cool. Even cooking oil. All right. There are a couple of things I need you to be aware of on your machine, which are your sensors, your limit sensors. This is the limit sensor for the Z-axis. This is the sensor that tells it that, hey, listen, you've reached the highest position. So you see, when this sensor comes in front of this, it will stop. It will write Z soft. It means soft limit, telling you that, hey, man, I can't do anything else. I've reached my maximum position. Can you undo that stop button there? All right. We'll come to the USB disk. So if I'm pushing Z down, if I move it up, check something. Wait, it doesn't read the sensor. Anyway, I think it's because I've hit the stop. I will fix that now. Okay, cool. Machines can shock you every time. Right, from here, you have sensor number one. Don't know what you're going to do with it now. You also have sensor number two, which is here. Do you see it? So that when it gets to this point here, there's this screw here. It's going to read this, and then it's going to stop. You have the same thing for the x-axis, and you will find it somewhere here. There we go, perfect. When it reaches that gear there, it will say, hey, look, you've reached the limit. And I think I know why it's not going to stop now, because of the stop that we had pressed. So there we go. It was supposed to say soft limit, but as long as we're still in that stop mode there, we are out, but we just need to, I'll show you how to recalibrate it so that it remembers all its sensors. Right, so with that being noted, you have the limits for Y, X, and Z. Before you do any job, it's very important that you do what is called homing. Homing is where you tell your machine to go to the zero position. Only when you do that can the machine be able to sense and know how big it is and all of that. It uses, once it knows 0, then it can start counting. It's okay, I can do 1.3 there, I can do 2.5 here. So this is your remote, right? I'm going to turn the machine off and we're going to start everything. If you check on the side there, there's a switch. Yeah, off. There we go. Everything is off. The machine is completely off. This remote here can stick onto anything metallic. So let's turn the machine on. There we go. Now, once the machine is on, this is a Wei Hong system. There's so many other Chinese systems, but the main one in the market, as I've noticed, is Rich Auto and Wei Hong. It's just a system like how you have Shenyang for that system, Hoson Soft, all of that. It's just a control system. Then it asks me, back to reference point. This means, do you want me to come back to the homing position? There is never a chance. I can escape this and start using everything normally, right? But there's never a time the machine will say, I want to start a job, and it will start cutting without it homing. It will actually say, no, I can't. So how do you home it? Now, if you take your remote, just to show you, you have X plus, which goes, that makes sense, right? Where do you think Y plus is going to go? There we go. Where do you think Z plus is going to go? Z minus? Cool. With this big known, where do you think 0, 0 for everything is? For X and Y, where is it? And for Z, is it up or down? You get it. So now with your remote, see this sign here? This is what is called origin position. This is what is called machine reference. And then you see this 0, 0 here. This is job reference. So there are two coordinate systems or two starting positions. There's a starting position for the machine itself. Then for every job that we say we want to start here, the machine will never forget that starting position until someone changes it. So if I want to go back to my job starting position, I press this one. But if I want to go back to the machine origin position, I press this one. Did I confuse anyone there?
This is the machine. This is
The job. Perfect. Now, for me to go back to the machine, any button that is inside the code, the shadow here, if you just press this, it won't go. I have to press Shift and that.
You want it.
Yes. So if I hold Shift and then I press this, then it asks, do you want to go back? Remember, that's the question it asked when I started. And now I say, okay. So first things first, you're gonna see the Z, you see, triggers. This noise that you hear, it's simply because one of these covers is not tight. That's all. But it's not a big deal. And now you can see it's moving, right? When I say oiling, someone will be pressing buttons and one will be pumping until the oil is, there we go. It always explodes. There we go. Can I get a cloth? There's a cloth. Yeah, no, it's just, it always gets out of the really here. No, I should try this end here. There we go. Let's get a, I'll get a pliers to tighten this because that's typical. Okay, cool. So do you see what has happened? It has homed how many X's? 3. Y, which is there, X, and then the Z. With everything being homed now, I can be able to set my starting position for the job. Okay, cool. That sucks. Where is the remote? Okay, here we go. All right, gents. Now let's go to the next part. From here, a few key things. I want to set my starting position to here. But remember, this is not the board that I'm going to be using. This is called a spoil board or a spill board. The point of this is to hold the material. So I'm going to take a material that is there and I'm going to put double-sided tape and layer my material on top. Right? But for me, let's say to firstly set the X and Y starting position, I simply move the bit where I want it. Let's say I want it somewhere there. It depends where I'm going to put my material, of course. And then I can drop my Z just to be able to see what's happening. So let's say I'll put my material and I'll be starting from here. It's up to me really, or I can move it a bit more. It's all up to me. If I want now 0, do you see every time I move Y, the Y increases. Every time I move X, the X increases or decreases. So how do I set it? You press Shift and remember the origin that we talked about. So it's Shift and this. Basically what this did it brought it back to the last set origin position. So I'm going to do this, my mistake. It's XY0. So see these values now. Clear XY coordinates. Okay, now it is set.
That's our new origin.
That's your new origin. So this is to set it. This is to go back to it. Are you with me? I'm going to give you the remote soon, but I need you to make sure you understand it. The best part about everything I'm saying now is it's all written here. Yeah. So I'm just running you through something, but if you ever forget, just read the back of the panel. So 3 things we say are crucial. We set the origin. We haven't set the Z one because I haven't put the material. We always set the Z on top of the material. We have a 2 presetter that we can use. It normally is not accurate, but let's say it is. Ideally, the way you set your Z is using a paper. If I can get any form of paper, any bond, yeah, even here, perfect. So you take any paper, then you bring it here, and then you start dropping your Z. But you see that dropping is too fast. So I get as close as I can to the paper. I've already touched it, I can't now. So I get as close as I can to the paper. And then you change your Z from, you see right now it's doing what I call, it's moving as long as I'm pressing, right? I need to change that from jogging to stepping. Make sense? And then now I'm going to set the thickness of the step, or the distance that it steps with. So here when I come to step, jog, step, I simply press shift. Jog, step, jog, step. So now I want to come to step. And how do I now set the distance? You press OK. When you press OK, you're going to see this function here, step Z. So which means it's moving 1 millimeter for every step that I take. So let's say I wanted to move half a millimeter, which I then go to this and 0.5. And then OK. Escape. I come back to the home here. So now what this does is, as long as it's on step, you see what it does now.
I'm not supposed to be spinning.
Sorry?
Isn't it supposed to be running?
No. And I still feel like this is a bit too much speed, so I can drop this one again, right? Okay, to 0.2. Okay. Now I have very small steps which allow me to be right. So as long as I can still move my paper, I'm not zero. When I do this, something like this, yeah, that's home. That's my zero. I might just want to set it again to 0.1. Right. Okay, I think that's better. Yes, there we go. Now, exactly. You see here, it's actually cutting my paper, which means it's exactly there. That's where I want it. From here, then I simply XY0, but if I want Z0, what do I do? Shift and do you want to zero the Z? Then I say, okay. You're with me? You're going to do this for your material. So I'm not going to bring the Z up again, but you see now it's not moving. Why?
Because you are stepping.
I'm stepping. So how do I move from step? Shift. And then now I'm jogging. Now it comes up. Are you scared? All right. So I'm just going to reset this Z so that it doesn't come down. We're going to put material. But before that, what else would be important for you to understand? A couple of things. You understand x plus x minus, y plus y minus, z plus z minus. Are you clear on the axis movement? You know how to set your origin position. You know how to come to the machine origin. Which one is machine origin? Good. And then job origin. This is not how you set, right? This is how you go back to it. So maybe I moved it and I've put another material, but I know that I've arranged everything, right? Maybe I draw like a 90-degree angle where everything I take, I simply put it here. So I move this to load my material. Then I want to come back exactly here. I simply just shift and then it will come to that position. It was already there. That's why it's 0, 0, then 10. Okay, cool. Understood? Right. Now, next thing is, you know how to set your XY0?
Yeah.
Which one is it? And how to set your Z?
It's
Same button for setting XY, shift and that. Perfect. Okay, those are the basic functions. The next things I'm going to show you are not intrinsic to operation, but they're important for you to know. First thing is my bit. If you are sure that your bit is tight and everything is fine, first thing I'm going to do is I'm going to turn on my, do you see it here? It has an on button in the router bit. It's rotating. You see my bit? You can't even see the spirals anymore, right? It's rotating. I told you that you can increase and decrease the speed here of feed rate and spindle, right? How do you do that? You see right now it says speed 7S spindle. Spindle speed is called S. Even when you check the G code, if you write S25, S what, it's simply telling you the spindle speed. So how do I increase and decrease it? You see here there is a plus and a minus for the spindle. On the same button, there's a plus and minus for the feed. So if I just press it as it is, it's about the speed, the machine movement. I can drop and increase the speed by pressing this up and down. But if I want to reduce the speed of the spindle, I have to press shift 6S. Remember that thing you were checking that side where you had 400, which was frequency, and then it came to 350, came to 250. That's the frequency which is controlling this. The chiller. No, the chiller is not cheaper. I'll tell you on when we're starting to do the cutting. Right. And then what's the next thing? We go to shift minus 4. As long as I press shift first, all of these are speeds I can use. depending on what I'm cutting. Ideally, people start on speed 7. So let's say I start on speed 6 from this my side. When the job is running, I can actually be increasing or decreasing. I'm going to set it to ignore the code that comes from there, and then you'll be able to control it here, checking on what's happening. That's actually more important. You can't tell much from the computer. You can only tell when it's on the ground. Okay, to turn it off, simply off. Okay. Next thing, it's auxiliary components that we talked about. Yes, I know we talked about this system, right? The other system we did not talk about is the chiller, which cools the spindle. I'm just running now; it doesn't really matter. But when I'm now cutting, and it now has resistance, I need to always make sure that the chiller, which cools the spindle, is running. Do you know where it is? Exactly, same thing. So your chiller has in and out, right? It's just circulation. Doesn't matter even if they rotate. This thing that you see here is basically a tool protector. What it does is when you want to start a job, it will tell you, no, I can't run the job because your chiller is off. Yeah. And then how do I turn it on? It has an on and off switch. Wonderful. Now I'm going to be putting the this is the let me get it. Yeah. All right. I think it's 540 something. Am I correct?
It's 250.
It's
540.
all right. So we're going to put double-sided tape first, so that we put our material on top. Okay. There are two ways that you can put your material here. If you had a vacuum table, it would be simple. You would simply take this, turn on the vacuum pump, and just put the material would hold. But this is a clamping table. So with the clamping table, we're clamping this, and then we put the board on top. Double-sided tape is one way. The best way is a drill. You hit the corners, and it's fastened. Right. So if you can help me, my man, go along the whole line. I don't know how long this thing, but I think it's as long as this is. So let me give you 2 or 3 of these, and then you can just jump on top. And then feel free to step on the machine, my man. Trust me, nothing is going to happen. That's what it's for. It's a heavy-duty machine. It's supposed to do that. Yeah, it's 2 of them. There you go. One small tip on putting material, you want to put both on both the X and the Y, because when it's moving, so that it has resistance on both sides. I'm gonna
How would you cut in the center?
Huh? How would?
Where do you remove the tape?
I don't know what I didn't think about that. But we will sort it out now. So you actually think about it. Do this. oil spray. I just want to grease my ear. I don't know about this one. Let me just go get.
Yeah, we don't have.
Okay, it's fine. Jackson, that's all you wanted to take videos.
Yeah, I think you see this on the screen now.
You didn't see what?
This thing that is screen now. Oh, it's just cleaning the final.
No, it's just it's the final pass. It just puts fun just to polish any uneven surfaces. All right. I am really hoping you can hear me, so I'm going to shout a little bit more so that I can be a bit more audible. But behind this, we have our machine running. It's basically running a job where it's going to do two files or two parts, basically. The first two parts is basically going to be an engraving or pocketing pass, where it's going to write what we want to write on the part we're making. And then the last part it's going to do is it's going to do a cutout of everything on this CNC router. But with that happening, I'm just going to run you through the machine just to explain the basic components that constitute of such a machine that we have here. Okay, come along. As you already saw, the x-axis on that machine, which is how wide it is 1.3 meter. With a CNC router or a milling machine, you can get as wide as 5 meters or even longer. It's all up to you what you decide. But ideally, the market has 1.3 by 2.5. You have a 300 by 500, 200 by 2 meters by 3 meters as well. And you have a 6090, which is basically 600 millimeters by 900 millimeters. Now, what you have here is basically a dust collector. The point of this system here is to take out all of the dust that the machine is taking out when it is doing the cutting, and then it collects it in these dust bags here. Come along. If you can come this side, you will see the pipe that I have here, which of course we haven't connected yet. It's basically a pipe that goes into the dust collection system to take out all of the dust that we have. This is the lubrication system where if we run it, it's going to push oil, which is going to run through all of this gear rails here to make sure that the machine is always oiled. All right. Now, in case you might be wondering, why do I have two boards on top of each other? Is this not a waste? No, not really. What happens is you have what you call a spoil board or waste or a spill board, right? Or sacrificial material. That's the name they give it. On this material, this is what we're going to use as a mat for us to then place the material that we are actually working on. With that being noted, there are plenty ways to attach this. You can have a vacuum table. With the vacuum table, you simply have a vacuum to suck through. But with the clamping table, you clamp your sacrificial material and you can drill your material into the spill board or into the sacrificial material. In this case, however, we are using double-sided tape, which is what we put here. And as you can see, the material is stable. All right. You have this box that you see here. This is basically your control box. There isn't much to this box, but the whole idea is all your electronics, all your motors, the motherboard, which is the brains of the system, are all inside here. Now, not to shock you, there isn't a lot, but I just want you to have a sneak peek of what is happening inside here. Now, if you come along, there isn't much happening really. You have what you call an inverter. An inverter basically runs your spindle. That's the one which controls the motor on the spindle, which is rotating. Number one. Number two, you have 1, 2, 3, 4. These are called stepper motor drivers. The whole point on these things is to control the motors that are controlling the X and the Y axis, as well as the Z axis. So ideally, you have two which are for the Y axis, one for the x-axis and another one for the z-axis, constituting of all your three axes. Now, why does the y-axis need two motors? It's because it's the longer axis and it's carrying the entire gantry of the machine, which is that entire frame there. So ideally, one motor is not able to carry the y-axis because of the gantry load. That's why we need two motors controlled by these two stepper motor drivers. So inverter for the spindle motor, and then Y motors have the stepper motor controllers, and then X-axis and Z-axis. The main board you're going to see here is a Weihong board, which is the motherboard or the system that we're choosing to use to control the machine. Now, it's a basic board that has the brains that communicates when we send our G code or our CNC code. Here is a transformer where we basically put single-phase power, but it can be converted to three-phase so that it can run the spindle you hear behind it. Can you drop the feed rate? Feed rate. Okay. The other small part we have here is basically called a power supply. The whole point of this is a 24-volt supply. It receives 220 volts AC converted to DC, and it supplies the motherboard here. And apart from that, everything else is just circuitry. These are just my MCBs, which I'm using to control the switch, or the contactors, which I'm using to control everything. And that's pretty much it. That's my machine. All right. So this is the electronic part. And what we have here is a chiller. The whole point of a chiller is to cool that spindle, which is running the machine there. Right. With that being understood, we're going to go to the machine and see if the job we were cutting out has been completely cut. We did not calculate thoroughly, did we? Jackson, I know whose fault it is. Did it cut through though?
Yeah, it did.
Yeah. So the challenge is that's why you want to collect the dust here. Well, that's a shocker, but it's okay. We can do another one. So this is because of the double-sided tip. Now let's push the material back. Do we have a brush somewhere? All right. So your material has basically been cut, right? Thank you. That's actually what I want. Let me have that. Cool. Stop. It's cool. Just please place this for me. Just re-hook it on top there. Right. So you will want to also just know that ideally, when you're running the dust collector, it will suck all of this dust out. And the reason why you want it out is because of this dirt here. I know it looks like it's nothing, but for a router bit, it can actually massively increase the heat. Part of that noise comes from the resistance that is getting from this chaff here. Okay, so we call them, I don't know what they call it. I think they, how many cuts did we do? No, it didn't do one pass. It did one pass. We need to, so no, it's not. Ideally, we had to change the, no. Not at all. That's the G code which we need to just revise and understand. I don't think we understood that. Well, how many parts did it do here? Oh, wow, this is actually smooth. For the bit that we have, you see what that step over does. Okay, and with apart from that, let me get something sharp. You have a Caesar or something. Just need to check. Did it actually cut through? Sorry. Yeah, it actually cut through. I am somewhat of a legend in this field. All right. We're going to revise our code just to make sure that we double check on where we went wrong on the Z, because we needed to step it's actually dangerous that it went on one pass. So this is what we're going to use as our stool top. We're going to cut out another one. I don't think we need much more space. If we just set the 0 to be exactly here, I think we'll be able to achieve it, right? Because remember, we're cutting out, so that's also another thing. Yeah, now this is smooth. Don't worry, once you take it down, actually. All right. Okay, so let's bring the concept here. Can you bring those 3 metal pieces? This will be the final task. Maybe I'll come check on you guys to see if it's been done thoroughly. You have a welder in-house, yes? So you can see we've cut out a board here where we've put some words inside which have been profiled, and then we cut out the shape around it. You can see the cuts are very smooth. We're using a 6mm bit, and yeah, everything is very smooth. The plan is to make a small stool. Let's put your pieces here. How are you gonna arrange them? So you're gonna have 1, just bring them up, 2, and 3. Right. So we're going to weld these. Move it back a bit. Yeah, okay, cool, perfect. Right, once these are welded, then you take your plate and you put it on top. And ladies and gentlemen, you have a stool. So that's the whole point. Hopefully we're going to send you pictures of the finished product and you're going to be able to see it on the video. But would this be a hard task? It's very simple, guys. Do you think so? Here's a small thing I'd want you to do. I wanted you to mark these positions. And then what we do is we're going to chamfer tiny slots so that you can have this thing sit inside. You get what I mean? And you don't even have to use this. So what you simply do is on your design for the circle, you put center, you put 180 degrees. And then from the center, you go 180, 180, 180, 180. It's a 16 mil thing. Go 6 mils in, and then yeah. Huh? Oh yeah, 120. Yeah, 120. Sorry, 120. Yeah. So 120, 120, 120, and then you fit it through, and then you can have a product. Yes, exactly. Not your X1. Yeah.
I mean, all my questions have been answered.
Is it? I hope so. This is smooth. This is beautiful. Do you guys want to cut another piece, a proper one, and just leave everything ready? That's the other thing we want to measure on the depth. So there's something called pulse equivalence. It's 2 mils, are you sure? I wanted, I'll get, if there was a vernier in-house, I didn't bring my toolbox, I could measure. But it can always be fixed, not a big deal. Yeah, if this is a mil, then we're correct. We should be somewhere fine. But maybe about 1 millimeter out. All right. Yeah, but this is not 3 mils. Yeah. Okay, good. Do you guys want to try the same thing? Just fix you or what? Are you good? Do you want to try a cut from there? The same cut, just reoriginate there and then start it. Mikey, you want to try? Just set your Z and start. Guys, why are you so afraid of machines?
But we need to fix
Or XY, that's what I'm saying.
No, that's what, so even here, what else you want us to cut 1 pass? Like we did.
Oh yeah, we need to go fix the G code. Let's go fix it. You sure it cut once?
One cut.
Let's go fix the G code. Take the flash drive.
No.
Alright, so now you do see us cutting without the dust collection system. This is simply for the sake of training so that you can actually see what's happening. Can you stop again? Can you move it that side? Can you move it back a little bit? That's Y plus. Alright, so the whole point here is so that you can actually see thoroughly what's happening without this thing clouding everything that we want to see. So ideally when we're cutting, we're not going to have all of this dust to deal with. But for today, we're going to have to settle for this. Alright, so there we go. Look, I do this because apparently I'm a professional, but you're supposed to have protective wear when you work on these machines. Remember, you need masks, you need gloves, and you need glasses to cover your eyes. And preferably better shoes which are not Vans. Alright, let's get our material out. There we go. There we go. Perfect. Okay. And there's all. So this is going to be the top of the tool we're going to make. You're going to do the welding and hopefully we'll show you the finished product on the end of the video. But yeah, thank you guys. Good. So we have two parts here that we do, which is pocketing and sometimes people can add a third function. It won't be a third two part because it's the same thing as this, so you will just add it to the two part of cutting. Where maybe you want to hang it onto the wall, you put a small hole here so that you can put a screw and then you hang it to all this stuff. You've seen people making watches, it's a very cool concept that people have making. It's nice that we got the material, but you need to do it good. So you're going to write the name and design whatever you want here, and place the part and engrave, and then you buy those watches that you want it. But they have nothing, it's just bone, it's just a watch. It's just crocats. And then you do your design of the times and everything. You stick it there, then you put it properly and set everything. Yeah, that's the whole concept. But pretty much guys, questions, subtractions, additions, is there anything I say that you feel that from your past experience it's not true? Yeah.
You see there, there are preset shapes.
Preset shapes, yes.
Like we said, they can duplicate and become